follow me on this? All right, can somebody just help me with this one, do the math on it? Well, go ahead, you give it to me. Because what you need to do is, when you're doing this one, you gotta make sure, this is a complex number. So it has a magnitude and phase, and when you're doing this, there's another complex number, so you can do it in polar. Doesn't matter how you do it, just make sure you do it right. Did you get an answer for this? Did you get it? Anybody?
Answer, so the magnitude is 2.56 volts.
And you guys get that? 2.56? In the back there? You guys got that? All right. What angle?
And then the angle that I got was 14.86 degrees, but I'm not.
Is that the right angle?
It is if you don't include it.
It's what?
It's like negative 75 or something.
Negative 75 is the textbook answer if we didn't include the 90-degree angle. The actual results was negative 165.14.
From this calculation?
Yes.
In the textbook as well?
The textbook treated it like a cosine wave and didn't give it a 90-degree angle, so it was off by 90 degrees.
All right. So if you do that,
just changes the angle.
All right. I'm not really worried about the angle, but that's the right magnitude, correct?
Yes.
All right, that's how you do it. One other question about this. I wanted to just mention one thing. Now, there was a problem I gave you where it was a common mode choke, and it was hooked up. One way was in series, the other was what to create differential mode, the other was to create common mode. Did you all do that problem? Anybody have questions about that? Or not?
Yeah.
You got it? All right. I mean, that's a pretty straightforward problem if you realize what's common and what's differential. But I want to make sure that there's no uncertainty about this, because in Dr. Whitworth's book, he's pretty casual. It's a very, just one short little blurb on this, but you have to make sure that you get that model right. All right, now, I'll pick up where I left off last time. So we were doing, let me just recap where we are, what we have done. This will be on the next quiz. So, not today's quiz. When we went ahead, we started with a standard waveform, and I'm just kind of doing a recap here. It looked like this, and it's repetitive, right? And I went ahead and I said, this is going to be, we'll call it a voltage waveform, but it's probably better to call it a current sense. That, and then it had an on time of tau, it had a rise time, tau rise, and it had a fall time, but we're going to make tau fall and tau rise the same. We always take the fastest of that. Then it had a time over which it repeated itself called a period T. Everybody with me on that? That's where we started. Now what I did was I said that this waveform, because it is periodic, can be represented as a Fourier series, and it can be represented as a summation of some C of n e to the j n omega naught t from n equals minus infinity to infinity, where C of n is equal to 1 over the period times the integral from minus t over 2 to t over 2 of the waveform v of t e to the minus j n omega naught t dt. In this case, omega naught is just 2 pi over the period, the fundamental period. That's called the fundamental frequency. If it would be in radians per second, if you divide by 2 pi, it's in hertz, all right, or cycles per second. But that's the fundamental frequency. Now, when you go ahead and take derivatives on this, and I'll put the first one right under it, so you can see this. by the way, the duty cycle or the duty time is just tau over t. Y'all follow me on that, class? That's something you're familiar with, right? All right, take one derivative and I get this. This is v prime of t. And now, really what you have when you take a derivative, it's the slope of the line, right? So this slope is going to be a over, it's rise a over run tau rise. So it's going to have a height here of a over tau rise. Then it goes to 0, then it keeps going, and over here it goes down, and it goes to minus a over tau rise, and then goes over and it will repeat itself. And such. This is time, this is the first derivative, and I said that v prime of t is equal to the summation here from n equals minus infinity to infinity. Taking a time derivative, that just brings out the jn omega naught times c of n times e to the jn omega naught t, and here we can say that this is really equal to a summation from n equals minus infinity to infinity of some c of n prime times e to the jn omega naught t. Now, just follow me on this. So be clear on this now. When I have this, if I take a time derivative of that series, the only thing that is a function of time is the exponential. So if you take a derivative of e to the at, it's just a e to the at. So the a in this case is jn omega naught. You all follow me, class? On y again, right? Now, that right here is a simple coefficient that I'm calling c of n prime, where c of n prime is really jn omega naught times c of n. My real goal here is to get c of n, but I'm going to work at it by doing derivatives rather than integrations. That's my goal. So I've got this. Now that c of n prime right here is really equal to, since it is periodic, it's 1 over the period from time, really from minus t over 2 to t over 2 of, and that's v prime of t times e to the minus jn omega naught t dt. Now I'm just doing this for completeness. This isn't what we're going to do. We're not going to use those equations. Now I take one more derivative and I get impulses. Y'all follow me? Once I take another derivative of this, and I'll put it on this board, now I have this. This is the double prime. When you look at this, you know, whenever you take a derivative of a function with respect to time, and it goes from nothing to something, that is a delta function, or a Dirac delta, or an impulse function. You're familiar with that terminology. And you have to weigh that by the height difference, which is a over tau rise. So now we got a delta function here at 0, and that delta function has a height of a over tau rise. And it is a delta of t here. I'm just showing you this because it is a delta function. Now, keep going over here. What happens right here? There's your next transition, right? It goes from a over tau rise to 0, so it's negative. Same magnitude, opposite sign. Here, you get a delta function that happens at tau rise. And it's going to have a value here of minus a over tau rise. And it would be delta of t minus tau rise. Y'all follow me on that? It's just identifying a delta function at that point. Now you keep going, and once I hit this point, think about that. If that's tau, and you shift it to here, this point right here is actually tau. Now at tau, it goes down again, doesn't it? Right here? When t is tau, it goes from a value, I'm sorry, it goes from 0 to minus a over tau rise, right? So it's negative going. You follow me on that? Same magnitude. So let me make this more clear. This is going to have that value. This is going to have the same value. The value here is going to be minus a over tau rise. This occurs at tau, so it would be minus a over tau rise times delta of t minus tau rise. This occurs at tau, so it would be minus a over tau rise, delta of t minus tau. Then finally, when we get to this point right here, this point in time is going to be tau plus tau rise. Y'all follow me at that point? And now it goes positive. So here, at this point, which is gonna be at tau plus tau rise, now it goes positive, has a value of A over tau rise, and then it repeats itself. Do we all agree with that? It's periodic. So I've taken two-time derivatives, got that. And this is just for analysis purposes. Now this is gonna have a value of V of t equal to summation n equals minus infinity to infinity. Now I took two derivatives, now V double prime is departed. So it's the second derivative of t. Now this is going to be equal to j n omega naught, double, or really squared, times e to the j n omega naught t. That's the same thing as n equals minus infinity to infinity of some c of n double prime times e to the j n omega naught t. And here, my c of n double prime is equal to 1 over t, the integral from minus t over 2 to t over 2 of, now it's v double prime of t e to the minus j n omega naught t dt. And of course, c of n double prime is equal to j n omega naught right here, squared times c of n. Now, our goal is to get c of n on this. That's our real goal. You all follow the logic on this one. Take two derivatives. Now we're basically getting a Fourier series type of analysis. And here's why we did it. This will be very easy to compute in 1 second. That's the reason. So I'm going to erase this waveform and work over here for a second. So now over here, what we find out is, first I want to mention something about delta functions. First thing is the integral of a delta function dt from minus infinity to infinity is 1. The area under a delta function is 1. The only time the delta function has a value other than 0 is when the argument of the delta function is 0. Everybody follow me on that? So, knowing that, if I integrate from minus infinity to infinity of f of t times delta of t minus anything, alpha dt, this is nothing more than the value of f of t evaluated at where this turns on, where this becomes 0 at alpha. And remember, the area, if you integrate the delta function, it's only 1, right? So it's really going to be just f of alpha. It's simply, whenever the delta function turns on, you look at all the other things in that integration and evaluate them at that point in time and take them out as a single number. You all follow me? So, now what I can do is say, when I look at this right here, at Cn double prime, now I have this. I have C of n double prime is 1 over the period, right? And I'm integrating from minus t over 2. Really, it's over any period. Whatever this value is you start at, you end up at 1 period further. That's all it is. You could start at 0 and go to actually t, but the problem is there's going to be a transition 0. That's the reason I did it. At 0, you don't know. Is it on or off? It's the transition. Do you follow me? So you always move away from those transitional points. Now over here, I have A over tau rise is actually going to be the weight on all those delta functions. Do you all see it? Take a look at that double derivative. The first one turns on at t, right? The next one turns on where? And it's a minus, right? Delta of t minus tau rise. Do you all agree with that? Next one turns on where? T minus tau. Next one turns on at, and it's a plus, t minus quantity tau plus tau rise. And this is all times e to the minus j n omega naught t dt. Take a second, take a look at that and convince yourself. I've just replaced the v double prime with the actual delta function representation. So now what happens? By the way, I posted all this information, the PDF, if you look at it, it's up there. Has anybody seen that? Don't you have, so all this is laid out clearly and accurately in the information I put there, but this is real, this has to do with the real frequency domain analysis of digital waveforms. It's not just a, hand waving, well, it's about that. This way you'll understand the entire, all the components and how you do the MC analysis of any frequency. When you analyze this right here, what do you get? Well, you get all these coefficients. So you have A over T, and then you have tau rise, right? Now, this delta function turns on when? Take a look at it, guys. At T equals 0. So you evaluate when it's multiplying this at 0. What is e to the 0? 1. Where does this delta function turn on? You can read my writing. Can you see it in the back or not, guys? At T equals tau rise, right? So now I evaluate this function at tau rise, and I get minus e to the minus j n omega naught tau rise. What about this delta function? T equals tau, correct, class? I hope you can read my writing, even in the back. So then I evaluate this at tau. So it's going to be minus e to the minus j n omega naught tau. Finally, this one turns on at tau plus tau rise. Do you all follow? Can you all see it in the back there? Some people looking at their computers and phones. I'm trying to really make this point clear to you. This is an important thing. You understand how these delta functions are turning on and off and why we're doing this evaluation this way. So this is going to be plus e to the j, or e to the minus j, n omega naught quantity tau plus tau rise. Now that's C of n prime without doing any integration by parts twice or anything crazy. It's straightforward using derivative method. It's a very easy way to get to the answer. We can get C of n by simply dividing that by j and omega naught squared. You all follow me? Just from over there. Now, this right here is something we have to talk about before we do that. Here we have A over tau, tau rise. And if you look at this, you can factor that, whether you know that. You can factor it as 1 minus e to the minus j n omega naught times tau times 1 minus e to the minus j n omega naught tau rise. Now I'm going to stop for a second and let you take a look at this. See, if you divide this by this, you're going to find that becomes 1, and this term becomes e to the minus j, or minus e to the minus j n omega naught tau rise. And take a look at this. 1 times 1 gives you 1, right? 1 times e to the minus j n omega naught tau rise gives you that term. Then when you take e to the minus j n omega naught tau times 1, gets this term. Finally, the two last terms multiplied together give you this. Do y'all follow me? So it does factor. I'm going to erase this part. And again, this is all laid out in the information I posted. So now I come over here, and now what I'm going to do is reduce this to something I understand. Now, you remember Euler's identity. We had e to the j theta minus e to the minus j theta over 2j is equal to the sine of theta. Do y'all remember that? That's one of 3 Euler's typical definitions. The other is cosine, the other is the exponential expanded in terms of the cosine plus j sine. Now if I look at this, I can multiply this by 2j, and look what I got here when I mess with this a little bit more. I'm going to take these terms, I'm going to show you what I'm going to do. First term, 1 minus e to the minus j n omega naught tau, I'm going to say that's equal to, now I'm going to factor something out so I can put it in the form of that sign. So I factor out an e to the minus j n omega naught tau over 2. When I get that, I get e to the plus j n omega naught tau over 2 minus e to the minus j n omega naught tau over 2. Y'all follow me on that? The only thing I've done is taken out I'm factoring out something so the remainder can be put in terms of a sign. That means this term right here can become e to the minus j n omega naught tau over 2 times really 2j times the sine of n omega naught tau over 2. You all follow me on that? I'm just looking at this term by itself. That'll go back in there in a second. If I do the same thing for 1 minus e to the minus j n omega naught tau rise, what do you see happening? I'm going to do the same thing, going to pull out half an angle right there, right? Or an exponential with half angle, minus j n omega naught tau rise over 2, and I get e to the j n omega naught tau rise over 2 minus e to the minus j n omega naught tau rise over 2. And that simply is going to be e to the minus j n omega naught tau rise over 2 times 2j, and then it's going to be times the sine of n omega naught tau rise over 2. A lot of writing, but you all follow me what I'm doing. Trying to get this thing into functional forms, I understand. Everybody okay with this so far? You with me in the back? Now I'm going to take that, what I just put down there, replace it here, and then I'm going to condense the whole thing. Or try to at least. So over here, now I have really e to the minus j n omega naught over 2, and it's really tau plus tau rise, because you can add the exponentials there. It's that, and it's 2j squared, and then it's going to be the sine of n omega naught tau over 2 times the sine of n omega naught tau rise over 2, and I have that. You all with me, class? I've really taken care of this thing, factored it, got it into something. Sines I recognize. I understand what a sine wave looks like. I don't know what that looks like. At least, not without plotting. So, I'm not done yet, but I need this for you. Are you okay with me erasing this portion? Everybody? Now remember, that's C of n double prime. So, if I take a look at this, and if you have access to this information on the PDF I put there, you can literally follow the steps I'm going through on the PDF if you want. And I don't know. Do you have access to the PDF? I'm asking. Do you have access to the PDF? Is it the EMC 4 days? That's right. That's right. Can you go down to the point where we've got the delta functions, or it's towards the end of that, I think. See if I can help you out. We're right there. There we go, right? And we combine it. That's where we're at. That's it. It's on page 121 of the PDF. Okay, now this right here, C of n double prime is really j n omega naught squared times C of n. We want to get C of n, that's our goal. Right? Because that will give us the spectral voltage component at each frequency, and that's what we're after. Now I'm going to divide that by this, j n omega naught squared. So just bear with me. Okay, now I have that. Now I need some board, so I'm going to take this off. At the end of the day, you're going to find out this simplifies some fairly easy things. But right now, it seems like a kind of a nightmare. All right, now what I'm going to do is mention something about a function. How many know what the sinc function is? Sinc of x. You familiar with that? How many are? Sinc function has two definitions. One is it's the sine of pi x over pi x. That's one used a lot of times when they want the zeros to be in integer values, when x is like 1, 2, 3, 4. The other is sine x over x. This is the most common, I think. Sine x over x. This is the one we're going to use. Now, if you look at a sinc function, the way it actually looks like versus x, it starts at a value of 1. This is the sinc of x. And then, first 0 is at pi, next 0 is at 2 pi. Down here, the opposite direction, minus pi, and then minus 2 pi, it repeats itself. You all follow me on this, class? That's what a sinc function looks like. I come over here, and I notice something. I have the sine of n omega naught tau over 2, and if you look here, I have n omega naught. Let me just mention this so it'll kind of get rid of some things that are a bit distracting. You see how I have j squared down here and I have j squared there? Y'all follow me on that? So I'm going to get rid of the j, all right? Because it's just not going to help me. Now when I look at that, I need to get, I have sine of n omega naught tau over 2. I need an n omega naught over 2 down here. Do y'all see? I can take this, and I can make this divided by 2 from on top, and then I can go ahead and make it n omega naught over 2 again right there. Do y'all follow? Now, I also need a tau in here. There's a tau. The tau I can put right there and erase it from here. With me so far? And I need a t rise, right? Now I can put the tau rise here. And now what do you see happen? This thing right here, this is a sinc function, and this is a sinc function. I have two sinc functions now. Do y'all follow? So what I'm going to do is say now, this mess can be rendered a fairly easy thing to see. I can say now that C of n is equal to, I forgot a T in the capital, it's equal to A over T times this phase term, e to the minus j n omega naught over 2 times tau plus tau rise. And then it's going to be really times the sinc of n omega naught tau over 2 times the sinc of n omega naught tau rise over 2. And I have my C of n. Now what that does for me is, if I look at any, this is an exact solution. If I look at any given frequency component, and by that I mean in terms of the fundamental, usually they'll say at the 5th or 6th or 7th harmonic, what is the value of C of n? Well, you simply put n equals 7 if you want the 7th harmonic. Omega naught is 2 pi f. Do you all follow me? And you do it. Now this is exact. Here's how we keep simplifying it down to something to make a little more sense. First thing we do with this one is we know omega naught is 2 pi times f naught. F naught would be the fundamental, right? Well then I can reduce this and I can say C of n is equal to A over T, then a phase term, e to the minus j n. Omega naught is 2 pi f, so that leaves pi, and pi times f naught times tau plus tau rise. This becomes the sinc of, and now it's going to be n pi f naught tau. And this is going to be the sinc of n pi f naught tau rise. And that's C of n. Now that doesn't tell you a whole lot yet, but here's something important. A couple things I'm going to show you. We're going to get this thing down to something that's manageable. I may not be able to get it all done now, but I will get it out. So, when I take a look at this whole thing, and I examine these sinc functions, when you look at the sinc function, sine of x over x, the way they view this is for small values of x, well really you're basically around the 1 value. If you think the way the sinc function looks like this, right? as a value of 1. When you have small values of this argument x, it's about 1. Do y'all follow me on that? Class, it's about 1 for small values of x. And then what it looks like is, as you get larger and larger, there's a taper on this that's proportional to 1 over x. What it really looks is we could cap the maximum magnitude as just 1 over x for larger values. Do y'all follow me? Basically 1 over the argument. So, what we can say here for this particular thing, if we are taking a look at just the magnitude of that, the maximum magnitude versus frequency, and we wanted to put what's called an envelope. You're familiar with the term the envelope of a waveform? When you take like an AM modulated waveform, you'll have something very slowly varying, multiplying a very high frequency carrier, and you'll get something that looks like that. You all follow me? The envelope is the maximum value, where the maximum value is. Our envelope is basically 1 over x. So now if you plotted, this is how it's done, logarithm. This is the log of f on this scale, and you plotted this function. I'll do this right here, and I'll show you what I mean and how you get it. If we take a look at the sink of n f naught tau, n pi f naught tau. This is what they do. N pi f naught times tau. Now, here's how it's typically done. These values will be discrete frequencies. This would be f naught, 2f naught, 3f naught, and so forth. You all follow me? And you would have basically spikes, something like this. And it would be going down. It would be multiplied by that 1 over x type of effect. But don't worry about this. Here's how they do it. You don't care about that. We care about the envelope. So what they'll do is they'll say, let n f naught be replaced by simply f. So now we're going to take a look at this at all frequencies, the envelope. You all follow me in this class? We get rid of discrete values, and we're looking at it for any frequency. So now this becomes the sign, or the sink, pardon me, of f tau. Now we're going to go somewhere. Remember, when this argument is small, it's about 1. You follow me? And where it starts falling off is where really it would be where f becomes 1 over pi tau, or the argument is simply over pi. So this frequency is going to be 1 over, this frequency right here is 1 over pi tau. And at this point, this thing will start falling off as 1 over x. Now some of this stuff, you know, 1 over argument there, but it's going to fall off linearly, and it'll fall off in dB of the plot over here. I'll be clear about this one. I'm trying to shoehorn all this in before the quiz. This would be 20 times the log of the magnitude of that sink function of f tau. And there's a pi in here, there is a pi, my bad. So when f is really when pi f tau equals 1, really the sink of 1 is where the 3 dB point is on the sink function, where it starts coming down. So when that equals 1, or when f is equal to 1 over pi tau, that's the first break frequency, and it's coming down at minus 20 dB per decade. Okay, how many are with me sort of on this one? I'm just trying to show you what the frequency envelope would be, and that's the key thing to this whole thing. You can forget about the individual frequency values. If the exact values are of no interest, we care about worst case or the envelope. So what that means, when I look at that function right there, and I plot it versus frequency, and I'll do this on Monday, because I've got 10 minutes left. I'm trying to be fair to you about this. It's an easy quiz. I'm going to give you some things to read and some problems to do. I didn't get a chance to work the problems, but please do this for me for Monday. Because I need to finish this thing on Monday, and there's plenty to do.
Oh man, that's lucky.